Greetings everyone. We're going to be talking about systems that have many different interacting objects, impulse, and do more free body diagrams. So what happens when we have a system? We could take our solar system just as an example, but there are many other kinds of systems. You can even consider yourself one of these systems. You have all kinds of cells exerting contact forces on each other. You have electromagnetic. You have lots of stuff going on inside of you. But just for simplicity, what about our solar system? So how can we follow the total momentum of our solar system? There's all kinds of forces going on here. So what we could consider is how does, let's just call this capital P. So how does this total momentum of our system change in time? Well, we know that this is equal to just sum of all the forces in our system. And this P is a vector too. So let's separate this part right here. So this sum of the forces is actually the sum of all the forces on Mercury plus the sum of all the forces on Venus plus the Earth and everybody, and don't forget the Sun. So what is even this piece? All the forces that are on Mercury. The sum of the forces that are on Mercury is just equal to the sum of the external forces on Mercury plus the force of Venus on Mercury plus the force of the Earth on Mercury plus all the other planets and the Sun on Mercury. And we can do this for every single planet and the Sun, all the bodies in the system. But then we can plug this back in up here, so we're going to get our dp dt is going to be equal to basically this giant sum of all of our external forces on one plus all these interacting bodies. And then we're going to get all of our external forces on 2, and you get the picture. 1 on 2 plus 3 on 2 plus all these other forces that we have. But what we can take note here is that there's Newton's third law, which tells us that the force of 1 on 2 is equal to minus the force of 2 on 1. So this is every action there is an equal and opposite reactions. These are interacting pairs. So what this actually tells us is that this guy right here is going to end up canceling out this guy. This guy right here is going to cancel out this next term. So each of these internal force pairs are all going to cancel each other out, and all we're going to left up with is these sum of our external forces on 1 plus the sum of our external forces on 2, which is really just saying what is the sum of all of our external forces. And this is going to be equal to how our total momentum changes with time. So basically all this amounts to is saying that as long as we don't have any external forces on our system, we can't change the total momentum of the system. So this is a very powerful statement right here. But we can have all kinds of forces interacting inside the system, lots of things that we don't even know going on maybe. But as long as there aren't any external forces acting on the system, those internal forces won't change the total momentum of the system. It will have to be conserved. Only external forces can cause a change in the total momentum of the system. So why does a plate So why does a plate break if you drop it on tile, but not on the carpet? So here we have our plate. We're going to drop it from some height h. Here's our y equals 0. And this is plus y. So we have gravity pushing down on the plate, pulling down on the plate. And the plate is going to accelerate down, and then it's going to run into the surface. So why does it break on tile but not on the carpet? So right away we can start to think about how tile is different than carpet, because how the plate falls through the air doesn't depend on this tile or the carpet. The plate is going to end up with some, it has some initial energy, and then all that energy is going to be converted into kinetic energy. So that's your 1/2 mv squared. So this tells us that the velocity of the plate is going to be square root of 2gh. So right before the plate falls, it has some velocity. After it hits this tile or the carpet, there's going to be an interaction there. So let's just consider the tile. Here we have V going down, and this is our tile. And then let's just do over here is our carpet. So the difference between these two is going to be how the plate interacts with the tile or the carpet. For the tile, what's going to happen is this. Basically, the plate will have to deform as it's making contact with the tile, or the tile is going to have to deform. But these, since they're both very hard, this deformation, this delta x, so something's got to slow down this v, and it's got to go over some distance in order to slow down. It can't just stop immediately. But basically, this delta x is going to be very small. And a small delta x implies a small change in time. So basically, we could write out these kinematic equations, and you'll get something like Vf squared is V initial squared plus 2a delta x. Now this a is not g. This a is the acceleration of the plate as it's slowing down here. So the center mass is going to be here, at the radius of the plate, but then as the plate deforms, it's going to move down that small dx I was talking about. So this is that acceleration of the plate during this small time window right here. And it's going to reach some point which the velocity is 0. And then we're going to have v squared plus 2a delta x. So here we're going to have a is going to be v squared over 2x. So if this distance is very small, then this a is going to be very, very big. Okay. Another way of thinking about it is if this delta t is small, this is actually even easier to think about. This average acceleration is going to be v final minus v initial over this dt. So v final is going to be 0, so it's really just that v over delta t. So if delta t is small, then that a has to be very big. For the carpet, we have a nice squishy surface here. It's going to deform a lot. We're going to have a big delta x, basically. Not very large, but much larger than here. And again, a much larger delta t. So these sorts of things, small change in time, small change in distance for slowing things down, are going to make you have a very big acceleration. And we're going to talk more about this and how it deals with impulse. Before we looked at a bit more kinematic way of looking at this with our v squared equals v initial squared plus 2a delta x. But now we're going to take a slightly different approach by looking at this sort of problem in terms of the impulse. So the impulse is the change in momentum. And so this change in momentum is equal to the integral of the total sum of our forces dt. So this looks very confusing. But basically what this is telling us is that your change in impulse is equal to the area under this curve that you exerted some force. So force can change in time, like maybe with this racket as the tennis ball approaches. So it's moving in like this and gets closer. The contact force with the racket actually increases as a function of time and then decreases because the strings are stretching. And the more stretch, the more force. So this isn't exactly an average, a uniform force in time. So maybe the force builds up over time, maybe it's constant, but basically this change in impulse is going to be the area under this curve. So that's what we have here, is we're basically just summing up the area under this curve as a function of time. So this is the integral way of looking at it. But we could also consider a more discrete way, the average way of looking at it. So here you have your F average dt. So we could rearrange this to be delta p over delta t is F average. And so this is something that we're familiar with. We've just really rearranged this to give us our impulse. So your average force is going to be your average change in momentum and change in time. This just picks up the average force. So we can use this in many cases to look at how the momentum changes and give us some force if we know the contact time. Alright, so we have a bouncy ball. We're going to drop it from a height of 1 meter. Alright, here's our ball. We're going to drop that down onto some surface 1 meter. We have mg pushing down. Let's just make this plus x. Alright, so it bounces off our desk from a back to a height of 0.95 meters. And we have the mass of the ball. Great. So we're looking for impulse. So impulse is change in momentum. So if I want momentum, then I need to be thinking mass times velocity. So I need the velocity before and after this collision. So the ball falls this 1 meter. So let's just work out that case. So before the collision with my desk. So we can just use energy conservation. EI equals EF. And so what I'm going to end up with, initially I have all this potential energy. I have mgh. And then it's going to fall that 1 meter, converting all that potential energy into kinetic energy. 1/2 mv squared. So this gives me that v is equal to square root of 2gh. So here my initial, well, my before velocity is 4.43 meters per second. And I can also do this after the collision. After the collision is a little different. So what I'm thinking about is the ball just collided with my desk. Now it has some velocity. So this is my velocity initial in this case, and then it goes all the way back up to 0.95 meters. Alright, so here's my initial, here's my final. I'm going to work this out the same way. So initially, all I have is kinetic energy in my bouncy ball. And then all that's going to be converted into potential energy. So I have the same problem basically. So that V is equal to square root of 2gh. And so my V after the collision is going to be 4.32 meters per second squared. Meters per second. So now I can work out how my momentum changed. I can just plug in this guy and this guy, so my delta P is equal to mass V after, V before. And what I need to be careful of here is my sign. So here I was taking a square root, so I got a little sloppy. Here I said this is plus y, so here before the collision my velocity is down. So I actually need to think about that being a minus sign. So V after, so 0.015 kilograms times that 4.32 meters per second minus a negative 4.43. And what I'm going to end up with is 0.13 kilogram meters per second. That's my impulse. Alright, so what is the coefficient of restitution? That is this E, and what it is V relative after the collision divided by V relative before, and I just divide these two guys by each other and I'm going to get 0.975. So that's my coefficient of restitution. And now I know that it deforms and remains in contact with my desk for 2 milliseconds. So what is the average force on the ball during that time? So basically, I'm going to look at this. F average is equal to delta P over delta T. So what I'm doing is I'm sticking this, my impulse delivered to the ball from my desk, in this 2 milliseconds. What I'm going to get is 65 newtons of force. So my desk had to give an average force of 65 newtons. So you could work that out. That means that for this 2 milliseconds that the ball weighed, felt like it weighed 7 kilograms, basically. But only for a very short amount of time. So the desk delivered the 65 newtons of force on average during that 2 milliseconds to the ball in order to change its velocity from this minus 4.43 to this plus 4.32. Let's watch a video. Alright, that's 2 guys working very hard. So here we have our initial position of the car. And then now we have Professor Andreessen and myself pushing very hard on this car in order to move it along. And we end up pushing it all the way to here, basically. We end up pushing it from there to here, this distance right here. So we're going to count up these spaces, measure how far each space is, and we figured out that the time that it took us to do this is about 13 seconds. So let's figure out what was the average force that we exerted on this car. So my car has a mass of 1,500 kilograms. We pushed it a distance of 18 meters and did this over 13 seconds. So let's do a free body diagram on my car. So here's my car. We're exerting some force. This is FA. We know that there's some frictional force, right? And then the car accelerates in this direction. So I'm going to go ahead and make this my plus x direction. Alright. So when I look at the sum of my forces on the car, I'm going to get FA minus FF for friction is going to be equal to mass times acceleration of the car. Now, since I don't know the frictional coefficient of the wheels or anything, basically I'm just going to look for F net. So we're actually going to push harder on the car than I'm going to work out. So what we're looking for is we need to look at this A. Here we're going to have x is going to be equal to v initial t plus 1/2 a t squared. So then I'm going to basically solve for a, and that's going to be 2 times 18 all over 13 squared, which is 0.21 meters per second squared. So we weren't able to accelerate this car very fast. But the net force that we exerted on the car is going to be m times a. So this is going to give us 320 newtons of force. So then what is the impulse that we delivered to this car? So that's going to be our delta P. So since I would have to go back to these kinematics in order to figure out how fast is the car traveling at this point, I'd rather just use F net delta T. Just assuming this average force that we delivered, and then what was the change in time that went over this. So this is going to be our 320 newtons, and then times 13 seconds. This is going to give us 41550 kilograms meters per second. So this is the total impulse that we delivered. In our last problem, we have a thief who needs to lower a 50 kilogram safe onto her getaway vehicle. Her rope can only support 300 newtons, so we could go ahead and work out, what if she just dangled the safe from this rope? So we know that we'd have mass times gravity, and we know that we have tension on the rope, and that if we were just dangling it, then the acceleration is 0. So this would tell us that T, sum of the forces is going to be T minus mg, and that's going to be equal to 0. So then T is equal to mg, so then T is going to be equal to 9.8 times this, which will be greater than this number. So she can't just suspend this safe indefinitely. She's going to have to lower the safe with the rope, and she's going to have to be very careful how she lowers it, because of course if she lowers it too slowly or not at all, this tension is going to be greater than this 300 newtons. Alright, so let's draw out another free body diagram. So here's the force of gravity on the safe. We still have tension pulling back up, but in this case we have acceleration moving down. So we can go ahead and draw where's our plus x direction, and so now we can work out what are the sum of the forces on this safe. So here we have tension minus mass times gravity is going to be equal to mass times acceleration. In this case, acceleration I put going down, and that's really going to help me check on, did I do this right? Because I better get a positive acceleration here. I better get a negative acceleration here because I know that A actually should be going down. So the maximum tension I can have on the rope is this 300 newtons. And then now I'm going to have the mass of the safe times gravity is going to be equal to mass times acceleration. So then acceleration is equal to this 300 newtons minus mass of the safe. So this is my 50 kilograms. And then now divided by the mass of the safe, that 50 kilograms. So I'm going to get that. I have to lower the safe no slower than 3.8 meters per second squared. So if I have A less than minus 3.8 meters per second squared, so I'm dropping it faster than this, then I'm okay. T will be less than 300. And you can plug this in and check. If you have acceleration greater than this, minus 3.8 meters per second. So here you're dropping slower and here you're dropping faster. So if you drop it too slow, tension ends up being greater than this 300 newtons, and your rope breaks and crashes into your vehicle, and you get nabbed by the cops.